Welcome to my class 12 physics, chapter that is ray optics, and today we will discuss about relation between focal length and radius of curvature of a spherical mirror. Focal length means that is the distance between pole to focus, and we write that is small f, and the radius of curvature means that is the distance between pole to center of curvature, and for this we write that is capital R. Clear? And for the derivation, here first we draw the spherical mirror, that means concave and convex. First one, that is the concave, this one is the concave because your outer surface is silver coated and that is the non-reflecting surface. Your outer surface, that is the non-reflecting surface, and inner surface, this one is the inner surface is the reflecting surface. So that this type of mirror we write that is concave spherical mirror. Clear? Now this point is the center of the reflecting surface, so that this point is known as the pole P. Now I draw the principal axis. You know, principal axis is passing through the pole and perpendicular to the pole, perpendicular to the reflecting surface at pole. So that this is known as the principal axis. Now suppose this point is the focus of the concave mirror, this point is the center of curvature of the concave mirror. Now draw the incident ray, one incident ray. Suppose that is parallel to the principal axis. Incident ray is parallel to the principal axis. Then what happen? The incident ray meet at the point M. Suppose this point is M, and this point is known as the point of incidence. This point is known as the point of incidence because incident ray meet at this point on the reflecting surface, so that this point is known as the point of incidence. Then from the point of incidence, what happen? The ray is returned back into the same medium, and for this first we draw the normal to the reflecting surface at point M. This one is the normal, and you know normal is always passing through the center of curvature. Now this angle is 90 degree. Then this is the angle. This is the angle between normal and incident ray. We write that angle is equal to angle of incidence. For angle of incidence we write I, and in this case we write that is theta. That means in place of I, here we write theta. Clear? Then what happened? The ray is returned back into the same medium with equal angle, and the incident ray is parallel to the principal axis, so that the reflected ray must be passing through the focus. Clear? Then this angle is the angle of reflection, and the angle of reflection also we write theta, because you know angle of incidence is equal to angle of reflection. This is the laws of reflection, you know that I is equal to R, so that in this case in place of I we write theta, in place of R we also write theta. Then this total angle is equal to 2 theta, so that this angle also we write 2 theta, because your incident ray is parallel to the principal axis, so that if this angle is 2 theta, this angle also 2 theta, same thing. Here incident ray is parallel to the principal axis. If this angle is theta, then this angle is also theta. Clear? Now we draw a perpendicular from point M means point of incidence, to the principal axis, and the perpendicular or normal to the principal axis meet at this point, and we write that point suppose capital D. Clear? And this is the diagram for the concave mirror. Similarly, we draw for the convex. Here inner surface is silver coated. This is the inner surface. Inner surface is silver coated, and that is known as the non-reflecting surface. And outer surface, this is the outer surface is the reflecting surface. So that this type of spherical mirror is known as the convex spherical mirror. Clear? Here also this is the center of the reflecting surface, so that this point is known as the pole. We write that is pole. And the principal axis is passing through the pole. This one is the principal axis, this one is the principal axis. Clear? And here this point we write, suppose focus, this point we write, suppose that is the center of curvature. And we take a incident ray, and suppose the incident ray is parallel to the principal axis. This one is the incident ray. Incident is parallel to the principal axis, and the incident ray incident at this point, and this is the point of incidence, and point of incidence we write, suppose capital M, just like this. Clear? This one is the incident ray. Then what happened? At point M, first we draw a normal to the reflecting surface. This is the reflecting surface. We draw the normal, and you know normal must be passing through the center of curvature. So that we draw the normal. Normal means that is perpendicular to the reflecting surface. This is the normal. This one is the normal, and this is the angle. This is the angle between the normal and the incident ray. This is the angle between the normal, this one is the normal, this is the incident ray, and you know this angle we write I, or we also write theta, same thing. Then what happened? The ray is returned back into the same medium with equal angle, so that we draw the reflected ray. This one is the reflected ray, this one is the reflected ray, and here this is the angle of reflection. For angle of reflection we write R, and here also we write that is theta. That means in place of I we write theta, in place of R we also write theta. Then we extend the reflected ray in the backward direction, and you know the ray must be passing through the focus. Clear? And in case of convex, if incident ray is parallel to the principal axis, if we extend the reflected ray, the ray appears to meet at the focus. The ray appears to meet at the focus, but in case of concave, if incident ray is parallel to the principal axis, after reflection, the reflected ray actually meet at the focus. This is the difference. And here also, if this angle is equal to theta, this angle is equal to theta, and this angle is also theta. If this angle is theta, then this angle is theta. Same thing, just like your concave. And this total angle, your total angle, that is 2 theta, theta plus theta, and this line parallel to each other, so that this angle we write that is 2 theta. And you draw a perpendicular or normal from the point M to the principal axis. This is the perpendicular, and the perpendicular meet at the principal axis at point D. Clear? This is the diagram. And here we write MCP angle, MCP angle, that is equal to theta. In this case also same thing, MCP angle, this angle that is theta. Similarly, this angle that is 2 theta, that is MFP angle, MFP angle, that is twice of theta. Here also same thing, MFP angle, that is twice of theta. And look at the figure. Here 2 triangles are there. One is MCD triangle, MCD triangle, angle is theta. Another triangle, another right angle triangle, that is MFD triangle, that is MFD triangle, angle is 2 theta. And we calculate tan theta and tan 2 theta from these 2 triangles. So that first triangle, that is MCD triangle, MCD triangle, we write from triangle MCD we get tan theta is equal to, what is tan theta? Look at the figure. This angle is theta. For calculate tan theta, front side of the theta, that is MD divided by DC. We write MD divided by DC. And here you also know that the value of tan 0 degree is equal to 0. That means in place of 0, suppose we write theta. In place of 0 we write theta. And here if theta is small, in place of tan theta we write that is approximately theta. So that here we write for small angle tan theta is approximately equal to theta. So that this expression becomes, in place of tan theta we write theta is equal to MD divided by DC. This is equation number 1. Suppose similarly another triangle is there, another right angle triangle is there, that is MDF triangle. Here we calculate tan theta, and here theta is, that is the twice of theta. So that tan 2 theta is equal to MD divided by DF. Triangle is MDF. Triangle is MDF. From triangle MDF we get tan twice of theta is equal to front side of the angle. Front side of the angle, that is this one, MD divided by DF. We write MD divided by DF, and that implies in place of tan 2 theta for small angle, in place of tan 2 theta we write 2 theta. So that we write that is twice of theta is equal to MD divided by DF, and here theta is there. So that in place of theta we put this equation 1. In place of theta we put equation 1. That means this equation becomes now, that implies twice of, in place of theta we write MD by DC. We write MD divided by DC is equal to right hand side, that is MD by DF. We write that is MD divided by DF. Clear? And here in both the side MD is there, so that MD cancel with each other, and remaining is equal to, that implies we write 2 divided by DC is equal to 1 divided by DF. That implies we write here DC and DF is there. Look at the figure. Suppose theta is very small. If theta is very small, then what happens? Suppose theta is small. If theta is small, we draw the line just like this. Then this angle is theta. If theta is small, then this point is the M, and from this point we draw a perpendicular. We draw a normal to the principal axis, so that the perpendicular normal meet at this point. That means this point is the D point. That means D point is very close to the point P. If theta is very small, then D point is very close to the point P. P means pole. So that for small angle of theta, in place of D we write P. In place of D we write P. Here we write for small angle. For small angle, in place of a D we write P. So that DC is equal to, we write PC. Similarly, here DF is there. In place of DF we write that is PF. Clear? That is a special case. That means for small angle we write just like this. So that the equation becomes twice divided by, in place of DC we write PC is equal to 1 divided by, in place of DF we write PF. That implies twice divided by, what is PC? PC means P is a pole, C means that is the center of curvature. So that P to C, that is the radius of curvature. So that PC is equal to radius of curvature. Similarly, what is PF? F means focus. Pole to focus, this distance is known as the focal length. So that we write in this expression, in place of PC, we write that is the radius of curvature capital R. In place of PF, we write that is small f. That implies we multiply 2 into f. That means twice of f is equal to that is capital R. This is the relation. This is the relation between radius of curvature and focal length. That means twice of focal length is equal to radius of curvature. Or we also write that implies we take 2 to the right hand side. That means focal length is equal to half of the radius of curvature. Focal length is equal to half of the radius of curvature. If focal length is equal to half of the radius of curvature, then in case of spherical mirror that may be convex, may be concave, your focus is just situated in between pole and center of curvature. Focus is the middle point. Focus is the middle point of the pole and center of curvature, because twice of focus is equal to radius of curvature. And this is all about your relation between focal length and radius of curvature in case of a spherical mirror. Clear? And in the next class, we will discuss about position, nature and size of the image formed by a spherical mirror. Clear?